Hi, in this session we will discuss about analysis of parallel RL, RC and RLC circuit. In last class we saw when we connect R, L and C components in series how the circuit behaves, that is what is the relationship between voltage and current, and also the different ways of expressing the power. Now let us continue our discussion on parallel AC circuits. That is when we connect RL, RC and RLC components in parallel, what will be the relationship between voltage, current and also on the power. Let us start with the parallel RL circuit. Here when we connect R and L components in parallel, the circuit looks like this. And for this AC circuit, the given applied voltage, let us take it as V, due to which the current flowing through the circuit is I, and at this particular node point, this current gets divided between R and L. Therefore, current flowing through R, let us call it as IR, and which is V by R. And current flowing through L, let us call it as IL, which is V by J into XL, where XL is an inductive reactance, or XL can also be represented as omega into L. So, by applying KCL at this particular node or junction, we can write I as IR plus IL. And here again, since it is an AC component, we have to consider an vector addition rather than simple arithmetic addition. Okay. Now, by substituting the value of IR and IL in this expression, we can write I as V by R plus V by J omega L. Here, V is a common parameter, so let us take V as common into 1 by R plus 1 by J omega L, or we can also write I as V into Y, where Y is nothing but complex admittance of parallel circuit. We say Y is nothing but complex admittance of the parallel circuit, where Y can be written as 1 by R plus 1 by J omega L, or let us take J to numerator, so it becomes 1 by R minus J times 1 by omega L. So this real part of Y, that is 1 by R, we call it as conductance and let us represent with G, and imaginary part, that is 1 by omega L, we call it as susceptance and let us represent it with B. Therefore, Y can also be written as G plus JB. And in order to analyze the relationship of I with V, let us take the phase angle of this Y. So, the phase angle for Y can be taken as tan inverse of imaginary part by real part. Therefore, theta is equal to tan inverse of imaginary part is this one, 1 by omega L, here it should be minus, divided by 1 by R. Therefore, which is also be written as tan inverse of minus R by omega L. So, by looking into this, what we can say, the phase angle for this admittance, complex admittance is negative. Therefore, current lags the voltage by an angle of theta. Okay. So, from this equation 2, what we can say, since I is V into Y, so by knowing the phase angle of Y, we can just conclude that if the phase angle of Y is positive, then it indicates that the particular component leads, and if the phase angle is negative, it indicates the quantity lags. Here in this case, the phase angle for y is negative. Here tan inverse of minus r by omega L. Therefore, this negative value will indicate that current lags the voltage by an angle of theta. Hence, we can say when RL components are connected in parallel in such circuit, current always lags the voltage by theta, where theta is tan inverse of minus r by omega L. And a phasor diagram of such a behavior can be represented in this way. So we know that in order to write the phasor diagram, always first step is just identify the common parameter. In this expression for I, the common parameter is V. Therefore, we represent V along x-axis. We represent V along x-axis, and for IR, we know that current and voltages are in phase. Therefore, IR vector should be along V, and IL, it lags the voltage. Therefore, we will represent IL vertically downward with an angle of 90 degree. And from equation 2, we also concluded that the relationship between applied voltage and the current is that current lags the voltage by V. Therefore, here I lags V by an angle of theta. Therefore, I we have written downward and V is written along the x-axis, and we have shown the phase difference between V and I as theta, which we will also come to know from this expression, that is I is equal to IR plus IL, that is resultant current of IR and IL. So if you take that one, then resultant of IR and IL we have to take diagonally, and by writing in such a way, we will come to know what is the relationship between I and V. I lags V by an angle of theta. Now let us see a parallel RC circuit. Here R and C components are connected in parallel. So again, we will carry our analysis in a similar manner. Let us take the applied voltage as V and current flowing through the circuit as I, and it gets divides through R and C. So let us represent current flowing through R as IR, which is V by R, and current flowing through C as IC, which is V by minus J into XC. Or XC is 1 divided by omega C, we can write. Or let us take this J2 numerator part, it becomes J V omega into C. So according to KCL, so we can write the expression for I is IR plus IC and substitute the value of IR and IC. So we can write the expression for I as V by R plus V J omega C. Here again V is a common parameter, we will take it outside and it can be written as V into Y. Again Y is a complex admittance, which is G plus JB. Here G is 1 by R and B is omega into C, where G is called as a conductance and B is called as susceptance. And from this we can write the phase angle for Y as tan inverse of imaginary part, that is omega C, divided by tan inverse of real part, that is 1 by R. So we can write theta as tan inverse of omega c by 1 by r tan inverse of r omega c. And from this we will come to know that the value of theta is positive. Positive in the sense the phase angle for the current is also positive, and hence current leads the voltage by an angle of theta. When RC components are connected in parallel, current leads the voltage by an angle of theta, whereas in parallel RL component, current lags the voltage by an angle of theta. So here we can write the vector diagram of such a leading current in this way. Again, here just have a look into this expression for I. V is a common parameter, so we have to take V along x-axis, and IR is in phase with V. Therefore, IR we will write along same line as V, and since IC leads V, we will write IC upward with an angle of plus 90 degree, and I is the resultant of IC and IR. We will write diagonally, and it indicates that I leads V with an angle of theta. That is, this I leads V with an angle of theta. Now let us see when all the three components R, L and C are connected in parallel, how the circuit behaves. So when RLC components are connected in parallel, let us take the current flowing through R, L and C as IR, IL and IC. IR is V by R, IL is V by XL or V by omega into L, and IC is V by omega C or V by 1 by omega C. So by applying KCL, we can write I as the vector addition of IR, IL and IC. Okay, IR, IL and IC. So substituting the value for IR, IL and IC, so we can write the expression for I as V into G plus J of YC minus YL, where Y is called as complex admittance of the circuit. Or we can also write Y as G plus J of YC minus YL, or magnitude of Y with an angle of tan inverse. Magnitude of Y is nothing but square root of G square plus YC minus YL whole square. Sorry, this is YC minus YL whole square, this term should be, and with an angle of tan inverse of YL minus YC by G. So here the phase angle value is 0 degree, and the resultant current phase angle is YC minus YL by 5, it is positive, and also it depends on the value of YC and YL. We will conclude how the circuit behaves. Okay, so combiningly we can write the phasor diagram for an RLC circuit in this way. Again, we have to follow the procedure to write the phasor diagram. That is, first identify the common parameter. In this case, V is the common parameter, therefore represent V along x-axis, and that is this way, and IR is in phase with V, represent along x-axis again, and IC is leads and IL lags, and depending on value of YC and YL, we can write the phasor diagrams. similar to series RLC circuit. That's it. Thank you.